Lecture 15, E141. So a couple of announcements for this week. Homework 6 is due next Monday. We extended the deadline because of E142 midterm. And please turn in your homeworks by 5 p.m. And that's when we are going to post solutions online next week on Monday. TVs are off. Okay, all good. For the review session today, I put a request for room, and that's still in the approval. Tentatively, it will be 6:30 tonight in 277 Corey, but I will have to confirm that later today. I'll put an announcement on the website and maybe even send the email to everyone to make sure that you all get informed. Do you have any questions about homeworks, project, lecture material from last time? Everything clear? All right. So what I'm going to do today is continue the story about logical effort and finally get into some more exciting logic styles. So now we are going to build some logic functions using various implementation strategies. And let me first revisit logical effort theory from last time. So basically we said that logical effort is a good method to estimate delay in logic gates and logic paths very quickly, and it relies on normalizing the gate delay to an inverter. Okay, so what we actually want to do is we want to express the gate delay, which is equal to tau gate times output capacitance to input capacitance ratio plus gamma of this gate. And then we say we want to still normalize this to the case of an inverter, to the time constant of an inverter. Where this time constant of a gate is equal to 0.69 times drive resistance times gate capacitance of this gate. Okay? So in this language over here, we know that tau gate times this gamma gate corresponds to Tp naught of a gate. Okay? Is this clear? All right. So now we are going to take this expression and write it in a really compact form by introducing some new terms. So first of all, we know that the logical effort, the way we define it, is basically the ratio of input gate capacitance of a gate to the input gate capacitance of an inverter that will basically have the same drive current. So we basically know that logical effort is equal to tau gate divided by tau inverter, and that is equal to drive resistance times gate capacitance of a gate times gate capacitance of an inverter. Now, by definition, we want to size this gate in a way that it has the same pull-up and pull-down resistance as an inverter. Therefore, drive resistances are equal. And basically, simply logical effort is equal to the gate capacitance ratio in that case. So you have simply CG gate divided by CG inverter. Okay? Because by definition we want to adjust the size of a complex gate such that it has the same drive current as an inverter. So it's basically if you put same load at the output you will get the same delay. But that will result in higher input capacitance because of the sizing of the gates. And you remember what we did last time for an AND, when we had a stack of 2 transistors, then we have to upsize the stack transistors to make sure that they have the same equivalent resistance. So that basically comes from that fact. This is just a pure definition of logical effort. And so this is an important term over here. So now this is our logical effort. Okay? The ratio of output to input capacitance is simply is called fan-out. Nothing surprising. And now it's interesting to see what this term equals to. Tau gate over tau inverter times the gamma gate. So we can write it this way. So we have tau gate divided by tau inverter times gamma of a gate. Now, tau gate is equal to R times gate capacitance of this gate. And gamma gate is equal to intrinsic capacitance of a gate divided by gate capacitance of a gate. And tau inverter is equal CG inverter. Okay? R goes away, and now we have the following. So now we have C intrinsic of a gate divided by C intrinsic of an inverter times C intrinsic of an inverter. I'm adding this term C intrinsic of an inverter divided by CG of an inverter. Okay, basically these two go away, and I'm just inserting this term over here, C intrinsic of an inverter. So what I have here, I call this term P. So this is equal to P times, and what is this term here? Gamma of an inverter, right? Now, this term here is called parasitic delay. And what parasitic delay is basically just the ratio of the total parasitic capacitance at the output of a gate to the total parasitic capacitance sitting at the output of an inverter. Simple as that. And in this logical effort formalism, you will have to basically do two things. You need to determine logical effort of a gate, and you need to determine this parasitic delay of a gate. That is basically a delay of this self-loaded gate without any external load. So it's basically TP0 for a gate. So what this basically tells you is that TP0 of a gate is P times larger than the TP0 of an inverter. And this makes sense because they have the same pull up and pull down resistance, only their capacitance ratio is P times larger. So you have P times more capacitance at the output than in the case of an inverter, and therefore you have P times larger delay because the resistance is the same. And that's all you need to remember basically to get started with this logical effort analysis. Is everybody clear with this? Questions? All right. So let's go to slides quickly. Thank you. So that's basically it. This is logical effort. That's simply ratio of the gate capacitances, and then you have this parasitic that is simply ratio of these intrinsic capacitances. So step number one, calculating logical effort. We said we are going to normalize everything to the reference case, which is an inverter. And we just need to start from this definition that logical effort is the ratio of the input capacitance to the input capacitance of an inverter delivering the same current. So now let's look at this case over here. We know that the inverter in the reference case has 2 times larger, wider PMOS than the NMOS for the same pull up and pull down. Therefore, the input capacitance of this inverter is equal to 2 plus 1, so that's 3. And we say that logical effort of an inverter is equal to 1 because we normalize everything to an inverter. This is by definition. Okay. Now let's take a look at the NAND gate. For the pull-up, we still have the same ratio of PMOS transistors, because in the worst case, only one transistor is conducting, and it has the same equivalent resistance as that of an inverter. For pull-down, however, we have to do a little bit of resizing to make sure that we have the same pull-down resistance. Since the pull-down resistance decreases with increasing transistor width, we have to upsize this to NMOS transistors to make R over 2, R over 2, to combine the total serial resistance equal to that of an inverter. Okay, so now once we do the sizing, we can compute logical effort of a NAND gate. So basically, looking at either input A or input B, we basically see what transistors are connected to this input and what is the total gate capacitance we see looking from the input into the gate. So over here, let's say, look at the input A. So we have 2 from the PMOS, and we also have 2 from the NMOS. So it's total 4. Same thing for the input B. 2 from the PMOS, 2 from the NMOS, total 4. So now logical effort is, by definition, the ratio of this capacitance to the ratio of input capacitance of equivalent inverter. So you have 4 over 3. Okay? And then same thing for the NOR gate. Over here, we had to upsize the pull-up to make pull-up resistance equal to that of an inverter. So every time you have a serial connection of transistors, you have to upsize by the number of transistors you put in series. And in this case, the total capacitance looking into inputs A or B is equal to 5. Hence, logical effort is 5 over 3. Okay? Then second thing we need to do is calculate the parasitic delay. And again, we go by definition that parasitic delay is the ratio of intrinsic capacitance connected to the output of a gate and intrinsic capacitance connected at the output of an inverter that delivers the same drive current, same pull-up and pull-down resistance. So again, we look at this reference case and observe how much capacitance do we have connected at the output. We know that intrinsic capacitances are geometric capacitances, so again, we are going to scale them relative to the total transistor width. So over here we have 2 plus 1, so we say total intrinsic capacitance is 3 units. Okay? And then let's take a look at the NAND gate. At the NAND gate output we have 2 PMOS transistors and 1 NMOS transistor. So the total intrinsic capacitance is equivalent to 2 plus 2 plus 2, that is 6 transistor widths. And then we simply find the ratio between this reference case and our case over here. So we have 6 over 3, parasitic capacitance of an NAND is equal to 2. Okay? And then same thing for the NOR. Basically over here we have a PMOS and 2 parallel NMOSs. So the total parasitic capacitance is equal to 6. And now we divide by the total parasitic capacitance at the output of an inverter and find parasitic delay of a NOR. This means that basically parasitic delay of this NOR gate is 2 times larger than the parasitic delay of an inverter. Okay? And now once we do this for every gate, we can basically analyze propagation delay of a gate. We can also do gate sizing to optimize propagation delay of chain of gates. And that's what we are going to do next. So this is another way you can estimate this logical effort and parasitic delay from simulation data. So what you can do is set up an experiment and change the load at the output. And then measure the delay, normalized to this time constant of an inverter. So what you know is, from the logical effort theory, the delay of a gate expressed in these relative units, normalized to this time constant of an inverter, is simply equal to the sum of 2 terms. One term is this, what we called effort delay. That is a product of logical effort of a gate and a fan-out of a gate. And then the second term is this parasitic delay. So basically, parasitic delay is equal to delay of a gate when fan-out is equal to 0. And as you start adding more and more capacitance, you have this other term, effort delay. So that's how we plot these curves, basically. Intercept point between this normalized delay and fan-out is equal to 0 corresponds to the TP naught of a gate. And we say, by definition, for an inverter, we have this parasitic delay to equal to 1. Now, when we change the load, we know for an inverter, logical effort is equal to 1 by definition. Parasitic delay is also equal to 1, and delay is simply described by this line that is equal to 1 times the fan out plus 1. So you have a linear line with a slope of 1. Now, for the NAND gate, we know that logical effort is equal to 4 over 3. Remember, that's the ratio of input gate capacitances. We know that parasitic delay is equal to 2. That's the ratio of intrinsic capacitances connected at the output. And then finally, delay is equal logical effort times the fan out plus the parasitic delay. And then you can see basically clearly parasitic delay is equal to 2, and we have slope 4 over 3. So when you keep increasing output load, then you see that your NAND gate is actually struggling. Its delay is increasing at a higher rate than an inverter. And this is really important to understand. So that's what we're going to do. Let's do first a couple of examples and then see how we can handle multi-stage networks. So let's now estimate the delay of a fan-out of 4 inverter. And we want to, in particular, estimate a delay of this guy over here. Now we start from basic definitions. You remember, step 1, determine logical effort over gate. So what's the logical effort over here? 1, correct. So that's by definition. So now electrical effort, or just the fan out in this case is equal to 4, correct. And parasitic delay of an inverter, 1, right, by definition. Then finally, the stage delay is equal logical effort times the fan out plus this parasitic delay. So this is basically equal now to 5, this tau inverter units. Okay. So now we can extend this framework to analysis of multi-stage networks that may have heterogeneous gates. Now we are familiar with the buffer chain sizing example, but now let's assume that we can have different type of functions along the path. And what we can do is basically then say that delay of a path is equal to the sum of gate delays in all of the stages. So we go over all the stages, sum up parasitic delay, logical effort, and fan out. So let's forget this grayed out area for a moment over here. And then basically what we want to do is now the same metrics that we used to characterize our gate, we are going to extend to a path. So now we say that path electrical effort is simply the ratio of the total output capacitance and the input capacitance of a network. And you may have multiple gates in between these two. And then you have path logical effort, which is simply product of logical efforts of individual gates in the path. And those are the two numbers that you should remember. And this is basically just extension of the case that we had in buffer chain example, when we had basically the total load at the output divided by total load at the input. We take nth root of that if the number of stages is n, and we say, well, that's our optimal fan out. But we have this additional term here for logical effort. That's what we need to worry about, okay? And then you can simply express the delay as the sum of all these stage delays. And now you know that the product of this fan out and logical effort, now we call that stage effort. We had basically just the fan out in the previous case when you had inverter chain, but now we have to sort of include this logical effort of a gate just to see how good that gate is at driving the load. Now what we are going to do is basically we say, just as in an inverter case, we say that optimum delay is achieved when each stage along the chain has the same effort. Okay, just as an inverter case. In inverter case, you remember we had that minimum delay is achieved when all stages have equal fan out. Now in this case, we say that minimum delay is achieved when all stages have the same stage effort. And the stage effort is product of that fan out that we are familiar with, and now this new metric that we introduced, logical effort. And simply then we can say that stage effort is nth root of this path effort that is calculated as a product of logical effort of all stages and the total output to input capacitance. That's called path effort. Now, very important, what does this mean? This means that the fan out of each stage is equal to that optimal stage effort divided by logical effort. Now, what does this tell you? If you have more complex gate, for example, NAND gate, logical effort of an NAND gate is greater than 1. What does this mean? This means that in order to keep balance, you have to assign smaller fan out to your NAND gate than to an inverter. Because you see that NAND gate is not that good of a driver. So let's say then I'm not going to really load this gate very hard, because I know that the inverter can do better. So I'm sort of going to distribute the load in a way that I'm going to assign a lot of work to good gates, like inverters, and for the lazy guys, I'm just going to give them a little bit of effort. And this is very important to remember. Complex gates should drive smaller load. So that's, as a designer, you should really remember this. This is very, very important concept. So it deserves to be highlighted. Everybody understand this? Is this intuitively clear? Because what we are going to do here is basically just repeat over the same concepts and hierarchically expand. So if you don't understand any of the methodologies part, please don't hesitate to ask questions. And then again, just as in the case of an inverter, we have that the minimum path delay is simply equal to the sum of all of these delays. That is equal to n is the number of stages times the stage effort plus parasitic delay. So now let's do one example. Let me go over to overhead camera here. So let's assume that we have a path with different gates along the path. So we have an inverter, then we have an OR, and then we have an AND, and then we finally have another inverter over here. Let's say that the output load over here is 20, and the input capacitance to this one is 10. And there is things around, but let's just isolate this path over here. So what we need to do now is to determine optimum sizing factors x, y, and z. For this case, to get minimum delay. So now what we need to do is basically for each gate, we need to do two things. We need to determine logical effort, parasitic delay, and then using those we can basically write the total path delay. So now logical effort of an inverter is equal to 1. Logical effort of stage 2 is equal to 5 over 3. That is the 2-input NOR. Logical effort of stage 3 is equal to 4 over 3. And finally, logical effort of stage 4 is equal to 1. Now, we also need the fan out. Fan out of stage 1 is equal to x over 10. Fan out of stage 2 is equal to output capacitance is y, input capacitance is x. Fan out stage 3 is equal to z over y. And finally, fan out of stage 4 is equal to 20 over z. So first, what we need to do is compute path effort. We know that path effort is equal to a product logical effort of all stages times the fan out of all stages. So now this is equal to logical effort of the first stage is equal to 1. That is multiplied by the fan out, x over 10, times logical effort of the second stage is equal to 5 over 3 times y over x, third stage logical effort is 4 over 3, fan out is Z over Y. And final stage logical effort is 1, and then the fan out is 20 over Z. So this is equal to 400 over 90. Second, calculate optimal stage effort is equal to nth root of path effort. So that is equal to 4th root of 40 over 9. That is equal to 1.45. Now that we know this optimal stage effort, we are going to determine the optimum sizes of X, Y, and Z. Because we know that what we are going to do next, we know that the input capacitance is equal to output capacitance divided by this stage effort and also multiplied by this logical effort of a gate. All right. So let's now figure out optimal sizes. So we can start either from the input or from the output. We typically work backwards and calculate Z and then go back through the gate. Can I move this? Everybody has it? Okay. So now let's calculate Z. So we know that Z is equal to logical effort of an inverter is equal to 1 times the output capacitance is 20 and the optimum stage effort is 1.45. So Z comes to be 13.8. Now we work backwards and we calculate Y. Logical effort of an AND is equal to 4 over 3. And then we have output capacitance is equal to Z, and the stage effort is again 1.45. We get 12.7, and so on. We calculate X, NOR logical effort is 5 over 3, Y over stage effort 1.45, so that is 14.5. And then we finally can verify the input capacitance of the first stage just to make sure everything is consistent. Logical effort of an inverter is 1. And then output capacitance is X divided by stage effort is 1.45, and these two divided give 10, so we are done. Okay? Everybody clear with this? And then finally what we are going to do is basically calculate the delay. Now that we know all the parameters, we are able to calculate the delay. So delay is simply equal to the sum of all stage delays. So that is equal to 4 times stage effort, that is the effort delay, plus sum of all the parasitic delays. So remember we had inverter, then we had NOR, then we had NAND, and again inverter. So parasitic delay for this one is 1. Parasitic delay is 2, 2, 1. So we have 1 plus 2 plus 2 plus 1. So that is equal to 4 times 1.45 plus 6. That is equal to 11.8. And you are done. That is your minimum delay. Okay. Any questions? Okay, so you'll see a couple more examples in discussion sections next Monday about how do you size the gates and calculate logical effort. Now let's take one step further. Oftentimes you have a logic path, and at certain point you have basically some off-path business that you want to do with your signal. And to handle these cases, we will have to introduce new type of effort, branching effort. And what this basically tells you is that if you have your path, then the most of the useful current goes through the path that you're interested to optimize for delay, but also you have some off-path current. And in order to provide enough current for your path, you have to spend extra effort because you have to drive that guy that is taking you off-path. And that type of effort is called branching effort. So this is basically the situation that we may encounter. So we have an inverter. And let's say that this is our path over here. But we also have some things going off path. Okay? So now at this node, what we define is the ratio of this on-path capacitance divided by this C on path. And this is called branching effort for a gate. Okay? So let's now do one example to illustrate this. So let's assume that we have topology like this. The load is 90, load over gate size is 15, gate size is 5, and then we have another of 90. And let's say that we are interested in this path over here, blue one. So what is the total path? If you look at this path, what is the total logical effort on a path? So that is equal to logical effort of the stage 1. This is your stage 1 times logical effort of stage 2. What's the total logical effort? I guess 1. Correct, because you have inverter, inverter, so that's 1. Now, if you take an approach and basically just calculate your fan-out as 90 divided by 5 and say 18, and then you finally calculate your path effort to say that that is equal to the total output capacitance to the input capacitance, fan-out times logical effort, you get 18, and this is wrong. What you need to do is basically account for this branching. And to do that, you need to calculate these basically stage efforts. So if you say stage effort of a stage 1 is equal to the total fan-out, that is equal to 15 plus 15 from the off path divided by input capacitance of this guy. So that is equal to 6. Stage effort of stage 2 is simply equal to 90 divided by 15, and you multiply by 1 because that's the logical effort of an inverter, and that is equal to 6. So that gives you total path effort of 36. And not 18. Okay? And in general, when you're doing sizing, this is the situation that you have. So you basically have a stage I, and then have stage I plus 1. And then you have this branching factor, Bi, defined at the output of this stage. What this branching factor means that you have Bi identically sized parallel inverters over here. And you have to be careful about that, because in your project, when you branch off at the first stage, you're not going to have the same sizes. And then finally, when you calculate the size input capacitance of this guy, then you have that Ci is equal to Ci plus 1 times Bi, because that's the total fan out of this guy, divided by stage effort of the stage I and times logical effort of the stage I. Okay? And let's go back to slides. So in multi-stage networks, now we're going to add this branching effort. So you basically just need to add one more term to the analysis and mechanism that we did so far. So in order to calculate path effort, you need to multiply three things. You have to multiply your total output to input capacitance of a path, logical effort of all stages along the path, and also branching of all stages along the path. And then you finally calculate your path effort in this way. And again, you can use the same formula to find the path delay. So it's the sum of all parasitic delays and all effort delays. And notice that this fan-out factor is slightly different than was in the previous case because it does include the branching. Because you have this branching times the fan-out. And from here, then you can calculate optimum stage effort, you can calculate sizing of the gates, and finally delay. A couple notes over here. So basically, you have to be, you can use this theory, it's very good for first order calculations, but you have to be careful about this branching factor, because what branching assumes over here is that you have this ratio of the total capacitance, that's basically off path plus on path divided by this on path capacitance. If you fix your branching, you can't do sizing anymore, because, or you can, but you have to fix the ratio of the on path capacitance and off path capacitance, which isn't always the case. And in your project, you will see basically when you set free x1, x2, and x3, you can no longer use the concept of branching for that stage, because those will be independently sized. You cannot just say, well, because I don't know what is actually coming after that path. What is it loaded with? What is the delay constraint on that path? So I can't really make a fixed assumption that the ratio of capacitance on path and off path has to be a certain number. So you have to be very careful about that. And second, this theory really works well for the branching when you want to just compute the delay. If you have all the sizing fixed, you can basically define, okay, now I know my sizing are fixed and set. I can define my branching factor. I can easily and nicely calculate delay. Then in that case, this theory is bulletproof. But if you have to do some sizing optimization and then you have gates that branch off, then you have to be really careful. Then you have to see if really this concept of branching does apply. If you have perfectly symmetric case where you have everything totally symmetric, and then you know for sure that all the gates that branch have identical gate capacitance, fine, do this branching theory. Otherwise, you have to be very careful. And that's what you are going to learn in the project, how to optimize paths with various load that have the same delay constraint. And you will end up with different x1, x2, and x3. Okay? So let's do one more example over here with branching. So let's analyze this case when we have an AND and then finally we have so what we want to determine is, if we know that the input capacitance of this one is C, then we want to determine Y and Y over here and Z's that will minimize the delay. So in this case, we have perfectly symmetric case because we have equal load we have branching with the same type of gates, so y's and z's are the same. So now, in order to analyze this network, first thing we need to do, logical effort, right? So the total logical effort is a product of logical efforts of the stage 1, stage 2, and stage 3. Question?
Can we assume that that second y, I mean, on top of the bottom y, is also has the same type of branch out? I mean, it's the same potential?
Yes, that's not drawn here. That's a very good question, actually. If you assume, as I just mentioned a moment ago, if you don't know what is really coming off this path, and then you may have different delay constraint, then you have to do this y1 and y2, just to make sure you're doing really optimal case. If you just fix the sizes of y's and then say, well, I don't know, but I still, let me do the first order analysis, that is still okay, but it'll give you suboptimal solution. So in this case, it assumes that it has the same type of network following this output. That's a very good point. Thanks. So now the logical effort is basically logical effort of all these stages. So what's the logical effort in this case for a path? So for an AND, you have 4/3. First stage, second stage, third stage. So now what's the fan out? It's equal to the total output capacitance to the input capacitance. So that is 9. And let's say we are analyzing this path over here. Now, what's the branching effort? What's the branching effort over here? B1. B1 is equal to so let's go by definition. So that is on-path capacitance, that is Y. Off-path capacitance is Y divided by on-path capacitance. That's equal to 2. Okay? So that's 2. Branching over here, 3. Good. So that's how you carry this forward, and then you have 6. Finally, path effort is equal to logical effort times the fan out times the branching, and when you calculate that, it comes to 128. And then finally, you can now do estimation of the best stage effort that is simply equal to third root of path effort that is equal approximately 5. And then you can figure out the sizes working backwards. The size of Z is equal to output of Z. So you have logical effort times C out times branching divided by stage effort. Branching over here is equal to 1. C out is equal to 9C. Stage effort is 5. Logical effort is 4/3. So you end up with 2.4C. And then finally Y is equal to branching at this node is 3. Output capacitance is Z. Stage effort is 5. And logical effort is 4/3. You end up with 1.9C. And then finally you can calculate delay using this formula. Since you have the same delay in all the stages, your effort delay will be the same. So 3 times this stage effort plus parasitic delay of all these stages, which is 3 times 2 equal to 21. Okay? So basically we use the same formula that we used before. You have logical effort, output capacitance divided by the stage effort and times branching. Okay? So when you calculate Z, you have output capacitance is 9, stage effort is 5, that's what you calculated. Branching is equal to 1 because this doesn't branch anywhere. For the Y, this is your logical effort. This is your stage effort. This is your branching, and this is your C out. Okay? All right. Uh-huh.
Can you give an example if we have Y1 and Y2, like if they're not the same, then what would it actually look like?
Sure. So that's basically the same thing that you have in your project. So for your project, you will have a situation like this. You have 1, then you have x1. Let's just do 2 branches. x2, and then you say that this one branch is over here, let's say b is equal to 2, y1, and then you have 16, and b2, let's say this is 4, and then you have y2 is equal to 16. Okay? Okay, so in this case, what you have is basically that the total load after this stage and after this stage over here is different. So if you don't know sizes a priori, then you cannot really do your branching theory. But what you do know, okay, is that at the minimum delay case, all the stages should have the same effort, right? So if I know that, then I know that this would be D stage, this would be also D stage, and this would be also D stage, right? Does that make sense? Okay. So now let's calculate the delay of this stage. So we have stage effort is equal to 16 over y2. Let's forget about parasitic because it's the same in the inverter. And since in the top branch you also have to have the same thing, you have 16 over y1. So from here you conclude y1 is equal to y2 is equal to y. So that will get you a good start. So now let's see what's the delay of this stage. So you have, let's again forget about parasitic and assume that gamma factor is 1. x1 plus x2. And in this case, you have b times yk divided by xk. Now, since your y's are the same, right? So what you know is that your bk times y over xk is equal to 16 over y. And then from here, you will be able to figure out your optimal xk. So basically now you have that xk is equal to bk y squared over 16. And that will basically give you different x's over here, x1 and x2. You couldn't really do branching over here because this is in a sense branching over here because you have that the total fan out is equal x1 plus x2. Right? Because both paths are important now. But you don't know really what is the ratio of x1 and x2. You have to analyze this entire circuit jointly and then figure out what are the relationships in play that will provide equal delay in both stages and that is also minimal. Does this answer your question? All right. Make sure also if you write optimization programs that you set lower bound on sizing of the gates. And don't be surprised if you get slight mismatch in the stage delays, which may occur if one of the variables hit the lower bound. For example, if the optimal value for this one is 0.95, but you have to take 1, that will also impact resizing of the other gates to provide the same delay. So just make sure that you don't get surprised if you see that. Okay, good. Let's go back to slides. So this can also be applied and extended to other effects such as adding wires. So basically over here you would just have the small correction term for the total fan out. You will have fan out of a gate plus fan out of a wire and still carry on the analysis. So finally, to recap this, logical effort design flow requires you to do two things. Calculate logical effort, calculate the parasitic delay for each of the gates, then figure out branchings and fan out, calculate this path effort. Then from there you can estimate the best number of stages, you can compute the stage effort, and then determine the gate sizes using this general formula. You can read all this in this book, but I think this set of slides that you've seen in this class is all you need to know, and that's all you will find in this text. Okay? Any questions? All right. And by the way, just one more comment for the stage effort, which is very important. You can also look at these curves. If this is your inverter, and this is, for example, your NAND, and you just look at the stage effort and you just write the slopes. So basically, for the same stage effort, which means the delay, this gives you information about fan out. So the fan out that you can do with an inverter is higher than the fan out you can optimally drive with an NAND, which basically just gives you another way of explaining why you need to assign a little bit smaller load to lazy gates. Okay. So now let's get to the fun part of the course, and let's analyze a couple more logic families. So we learned in standard complementary CMOS that for the implementation of a function, we really need to implement the function twice. We have to have the pull-down network, we have to have pull-up network again that implements the same function but just covers different values, logic ones. So what the main problem with that is basically that it costs you too much of area. Because you know that for the NMOS network, let's say you have pull-up network, and then you have pull-down network, and this is your F bar. This is VDD. So now you know that area, it takes you some area and certain number of transistors to implement this function. For an N input function, you need N transistor here, you need N transistor here. So AP is 2 times AN, because PMOS transistors are worse at driving logic 0, approximately. So basically you have A, overhead in the number of transistors, and B, overhead in overall area that is required for the implementation. So for this reason, people started to look into alternative logic styles and say, well, you know, this pull-up network, I don't really like it, because it's very area consuming, and all it does basically it just implements the same function as the pull-down network. So the idea came up and say, well, how about if I pre-compute F at 1, and then I pull down when I need it? Say F is equal to 1 unless I pull it down with my pull-down network. And that's how people came to the idea to implement a function using this ratioed logic concept. And I have illustration for that in slides if we switch over. Thank you. So basically what this does is, let's say I have some resistive load to my pull-down network. I still implement the same pull-down function and pull this down to logic 0. I'm not going to say 0, but logic 0. Okay, you'll see that in a moment. And when my pull-down network is not pulling down, what I have is basically pulling up through this resistive load. And this resistive load really mimics sort of the pull-up resistance of your pull-up network. It has some value, okay? And what this gives you is basically obviously reduced implementation area, which was the main goal. But it also adds some negative effects. What happens with the noise margin in this case? What is the VOL equal to? What is the fundamental problem? Fundamental problem is that this one never turns off. So when you're pulling down, normally in the complementary CMOS, you have your pull-up disconnected. And you're happy pulling down. But now you have this guy working against you. And as a result, your VOL will be defined as a voltage divider between the equivalent resistance of a pull-down and this pull-up resistance. So you see that your VOL increases. So that is not good. What else is not good here? How about power? Static power, exactly. So that is also another penalty that you pay here. And there is various ways that you can implement this resistive load, and people were toying around with ideas. Let's see, what can I do? Now I'm aware of two problems, VOL and power consumption. Can I still use this logic style, but to basically reduce my implementation area, but sort of make a good compromise between power and noise margins? And this is called ratioed logic, because logic level is dependent upon ratio of the equivalent pull-down resistance and this load resistance. VOH is equal to VDD. VOL, looking at the DC characteristics now, is equal basically to this resistive divider, equivalent resistance of a pull-down divided by pull-down plus R load times VDD. And as a result, you have asymmetrical response. You no longer have standard complementary CMOS 0 VDD, but you have some VOL to VDD. Static power consumption is bad, and low to high delay, assuming that your switching threshold is in the middle between VOL and VDD, is 0.69 R load, C load. This is now how you can implement, some of the ways you can implement this load resistor. Basically, putting a discrete component is not really a good idea. You normally can implement good resistors using active devices, transistors. So you can use, for example, depletion load NMOS, which has implanted channel. You have to basically apply negative threshold to turn it off. So this one is always turned on in a diode connected configuration, but it's kind of requires extra processing steps and all these things. So just like, let's just use standard PMOS, CMOS process and see what we can do. So one idea is to use this pseudo-NMOS, where you have the PMOS that's always turned on as a load. And that's basically common approach to implement this logic style. So when the pull down is disconnected, you have this one pulling up to VDD. Otherwise, you have to fight this guy to pull down to VOL. Okay. This is now implementation of 4-input NAND function. So now you notice that you have a lot smaller area, because in the standard CMOS case, you always need 2 N transistors. In this case, you need N transistors for the pull down and 1 transistor for the pull up. So you need N plus 1. So it's almost 2x reduction that becomes available to you, especially when you have larger number of inputs than you have close to that 2x. Now, what you need to worry about is basically static power dissipation and ways you can cope with that. So obviously, you would like to size this transistor as large as possible for the propagation delay standpoint, but you also need it as small as possible to conduct least amount of current when pull-down network is pulling down to 0. And that's sort of a compromise. Another good thing about this is basically that the total self-loading capacitance at the output is now reduced, because you have fewer transistors connecting to your output. And now the issue becomes the sizing ratio of your pull-up and pull-down network. And you can readily compute this VOL, making a reasonable assumption that your transistors will be in a linear regime here, because you expect your VOL to be fairly low, as close to 0 as possible. And you can basically just equate currents and then figure out what would be your VOL depending on this sizing ratio of the PMOS and NMOS. And now you can play with this sizing ratio to sort of figure out the trade-off between propagation delay and static power consumption. Here's the result. If you plot your VTC characteristic and start with a very strong PMOS, so basically your VTC is not going to look good, because your NMOS is not going to be able to pull down enough. And then you spend most of the time at VOH, or close to VOH. So you're not going to be able to fight that PMOS and pull it down. And as you can see, as you make this PMOS weaker relative to the NMOS, then you have a nicer and nicer VTC because your pull down is strong enough to overpower your pull up and bring the voltage down to VOL, and you have nicer transfer characteristics. So that's the conclusion. This PMOS has to be fairly weak for the noise margin reasons. You can also adjust this PMOS load. This is one technique that is common in design practice. You can say, well, sometimes I need really to shift this VTC. Sometimes I'm really worried more about performance, sometimes more about static power. So basically, you can sort of adaptively change the load depending what you need to do. If you need to make a transition or if you need to just stay in the steady state. So you basically just say, well, my transition has finished, so let me decrease the current that I need to fight from the pull-up. And in that case, I have a good static power consumption. But next time you need to go transient regime, you say, well, I'm going to enter turbo mode. I'm going to turn on this other device and I'm going to pull up really fast. So this is actually the idea behind this active loads, where you can basically selectively enable or disable these transistors to play with the equivalent resistance of the pull-up network. Now, there is another idea. This still actually results in static power and noise margin issues. There is this other idea for improving the load that uses this, and now you will start seeing a lot of these acronyms for the rest of the class. This is DCVSL. This is called Differential Cascode Voltage Switch logic. So what actually happens here is that you have now no longer just a pull-down network driven by primary inputs A and B. So let's put it here so you can. So this is very important logic family. So you're going over various logic styles. Time to wake up. So again, you have PMOS, and then you have M1, M2. So this is now out bar. And you have two pull-down networks, pull-down network 1 and pull-down network 2. So now, a couple things over here. So first of all, now your pull-down networks are no longer driven by primary inputs, but also by their complementary values. And what you have over here is basically have two exclusive, mutually exclusive pull-down networks. So you basically have either pull-down one is active, so either this one is on and this one is off, or this one is off and this one is on. Okay? And then you have this cross-coupled stage at the output that kind of helps you recover logic levels. So you have, if you're taking E40, 140 this semester, so you would know how to analyze this feedback loop over here. So basically, let's start from gate signal over here. So you have phase shift of pi over here because that's an inverting case, and then you have another pi over here. So you have basically 360 degrees. That means it's a positive feedback. What this means is basically if this voltage goes up a little bit, then due to phase shift, this voltage is going to go down, but since this transistor is a gain stage, then you have a larger amplitude. Now, that signal now goes back to the gate of this guy, and it inverts again with even more gain. So basically you started with a small signal change over here. When you go around the loop, you end up with even bigger change. And this kind of feeds each other and establishes complementary levels. So now what you are doing here is basically a couple things. First of all, you are implementing both your true and complementary outputs in one stage at the same time. You remember in static complementary CMOS logic, if you have to implement AND function, you have to implement an AND, because your complementary CMOS is always implementing inverting function, plus another inverter stage. So that kind of has a long delay, and you need two gates, two stages to implement that function. Over in this case, you have not only implement function in one stage, but what is also true is that you have your true and complementary outputs available at the same time. And that is going to be clear in a moment. So what you have basically due to this feedback mechanism over here is that if your out goes like that, your out bar will go at the same time in other direction. If you had your AND function, for example, in standard CMOS, you basically have, if this is your out and this is your out bar, then you have basically out going like that and then out bar coming later. So this is when your out becomes available and this is when your out bar becomes available. So you have sort of timing mismatch between these values. And this can be useful in cases of certain functions, such as, for example, when you want to implement XORs. That is fairly useful and readily used in the implementations of adders, when you have basically a lot of XORs and then you have both true and complementary signals. And then we will see that in a moment. So basically, what you have here is two pull-down networks, but you also have true and complementary functions at the same time. For that, you need to drive with signals, not only primary inputs, but also their complements. So when this one is on, so this one is then pulling down, going towards 0. Then this transistor is then pulling up, and that turns off this transistor M1, and basically this one pulls down all the way to 0. So that's another good thing about this logic family. It basically pulls down all the way to logic 0. VOL is equal to 0, and that means improved noise margins, and there is also no DC current, static current at the steady state. You do have some extra current when you're fighting this feedback and switching, but that's basically just extra switching power that you need to spend. But at the same time, you implement two functions, true and complementary. Okay? Questions? All right, so this is one example of the logic family. If you go to slides. Yes?
Pull-down network could be any CMOS logic?
Pull-down network can be any CMOS logic, correct. We can implement various functions. We can do, here's one example. Here's XOR XNOR gate. So let's look at the output over here. So you have basically that your XOR is equal to AB bar or A bar B. That's basically exclusive OR. Whenever it's equal to 1, when one and only one of the inputs is equal to 1. So that's shown here. So you basically have a stack of A, B bar over here or A bar B. And you are implementing inverse of that because that's the pull down. Right? So now this is XNOR and now this is XOR. What you can also see from this example is that you can share transistors for reduced area. And basically you share bottom transistors A and A bar, and you can basically then just build on that and implement complementary function. So now let's do one example here to make this clear. How would you implement AND NAND function? Let's do AND NAND. in this CVSL. So now this is your pull-up structure. Let's say that this over here is out and this is NAND. Now, how would you implement NAND using NMOS transistors? If you have two input NAND, inputs A and B, what do? Series, right? So you just put two series transistors, A and B. And now you remember, for this CVSL, you also need to have another mutually exclusive pull-down network that also is driven with complementary input signals. What does this mean? So now I need to implement complementary output that will implement my AND function. So what do I know about AND? AND is equal A, B. But since I can only implement with pull-down inverting function, then I have to do this, right? Put two bars on top, because I can only implement something with big bar on top, right? So now what does this mean in terms of the Morgan principle is this is A bar or B bar bar. So what does this tell you? You have two transistors in parallel that are driven with these complementary signals. So this is your pull-down network, and this is your mutually exclusive pull-down network. So now let's assume that both inputs A and B go from 0, A and B go from 0 to 1. So that means A bar, B bar go from 1 to 0. So this means that basically this AND function was initially at 0, and it will go to 1, and this was initially at 1, and it will go to 0. So what you have now is basically that this NAND output will start changing. So let's see, if this one was at 1, this one was initially off, and if this one was at 0, this one was initially on, right? So now what you need to do is basically pull this one down enough below VDD minus VT, and as soon as that happens, this one goes from off to on when out is less than equal to VDD minus VTP. And when this one turns on, then the feedback mechanism kicks in, and it will basically start pulling this node up. So let's take a look at the timing diagram on the slide. So this is what happens basically. You have that your NAND starts pulling down, and as soon as you reach VDD minus VTP, then the feedback mechanism kicks in and this one starts to charge. And that happens rather quickly when both of these are working through this positive feedback, and then you have complementary and true outputs available at about the same time. Okay? Does this make sense? All right. Good. Oh, before we go to pass transistor logic, forgot to, yes.
How do you get the A and A bar together at the same time? The inputs.
You basically, that's a very good, that's excellent question. Thank you. So the question is, how do you get A and A bar going in opposite direction at the same time, right? So over here, you assume that your previous gates are also implemented in this CVSL. And they also have this kind of feedback mechanism, and then you assume that you have true and complementary outputs going in opposite direction at the same time. But that is very good introduction actually for the pass transistor logic, that we will see that that's another way of implementing these functions using also complementary signals, and we will see how they become available. But we assume that they come from the same type of logic gate. So next week I will be away on Tuesday and Wednesday, going to visit Intel Labs in Oregon, and Louis will substitute lecture, and he will teach you dynamic logic next time. And also I have another travel date that I know of so far on November 14th, which is Tuesday. I will be going to University of Michigan, and for that I will probably have a makeup class. We will have a lecture scheduled at some different time, and if you can make it, good. If not, there will be you can watch it online. So that's what I forgot to mention. And 14th, no 15th. Thanks, 15th. And office hours are today, 1 to 3. New office hours. All right. So let's now look into some other techniques that we can implement logic functions. So what we dealt so far with is basically every time we have like a pull up or pull down network, we can basically go to pull up or pull down, pulling up and pulling down to VDD or ground. So now let's move that restriction and say, what happens if we can basically have primary inputs not only driving our gate signals, but how about we can connect primary inputs to the source and drain, and sort of in that way we can provide functionality. And that's the idea behind this pass transistor logic. So it allows primary inputs to drive source and drain terminals. And the idea is again to reduce the number of transistors. So what you have in pass transistor is you have this switch network, which is basically just implement your transistors as switches, the pass gates. We've seen this structure in the previous lectures, so it's familiar to you. And what you have is basically you have gate signals controlled with certain voltages, and then you have source signals as well. So here's an example of an AND gate. So what do you know about AND function? So you know that your output should be equal to 1 when both A and B are equal to 1, right? So that's shown here basically. When B is equal to 1, I can pass A from the source. If A is equal to 0, then my function is also equal to 0. When A is equal to 1, my function is equal to 1. And then I can implement basically AND function in this form. But now the question is, okay, now I can implement this function with only one transistor. Why do I need this other branch? Why is it good for? How about if B is equal to 0? What will happen? You have your output floating. You have your node sort of very unstable. So that's why you need to actually do the full coverage and implement this function when you have B bar. So when B is equal to 0, then surely your function is going to be equal to 0. And that's what you have over here. So basically when B is equal to 1, your F is equal to A. And that's implemented with this transistor. When B is equal to 0, then your F is also equal to 0. And actually you can do this in a much simpler form. I used to do this a couple years ago to play with the pass transistor logic. And you can read the papers on my website if you're interested. But you can basically do this very easily with Carnot map. So you say A and B, 0 and 1. So you know that your logic function is 1 only when both of these are equal to 1. and the rest is 0. So now what you do is basically say, well, let's see what happens if, how can I cover this map using control signals A and B. So when you say, let's say my B is equal to 1, when B is equal to 1, B is equal to 1, then the function is equal to A, because A, when A is 0, function is 0, when A is 1, function is 1, and when B is equal to 0, I have to turn on this branch with B bar, and then when B is equal to 0, I'm covering this region of a map. So I have full coverage of a function, and this is my function, so I can put over here 0. Right? Or I can also put the value of B for that sake, because when B bar is equal to 1, B is equal to 0. And now the question is, as you just pointed out, that basically now the issue is to generate these complementary signals. And basically for the implementation of AND function, you need 2 plus 2 transistors, because you also need to provide this B bar if you assume that you can use inverter over here, or we will see later how you can basically do this in fully complementary form, such that you have aligned inputs switching at the same time, 2 and complementary. So this is 4 transistors, same number that you had in that's a great question, and that is basically dual pass transistor logic. We will see how you have various families. You have complementary pass transistor logic, NMOS only, dual pass transistor logic, both NMOS and PMOS. And you will hear about in the next lecture. All right, and I'll see you next week.